Switching gears here, I want to talk about different ways of expressing coefficients. This is highly variable across disciplines. There's a handout that I put together. There's a link to in the syllabus that explains all of this. So let me just summarize it. The ways that there are at least this many ways. One is raw score, right? We've already talked about that. That's just a simple change in y relative to 1 unit change in x, where raw refers to the raw units. We're not doing any transformation of those units. Effect sizes. Especially in experiments, take the change in y and then standardize it by dividing by the standard deviation of y. So that puts it in a metric that education people and developmental psychologists use a lot. There are rules about what constitutes a big effect size, the so-called Cohen rules, where 0.8 of a standard deviation is a big effect. 0.4, I think, is a medium effect. 0.2 is a small effect. We'll talk about why that doesn't make any sense, but it's a widely used kind of metric, and it keys off of a standardized difference, in this case, between the treatment and control group, compared to a 1 unit change in x. And in experiments, this is 1, 0, whether in the treatment group. All right, so that's nice. A 1 unit change is going from a 0 to a 1. In other words, going from being in the control group to being in the treatment group. And the regression that you run will estimate how much of a change that is. And if you take raw units and divide by the standard deviation of the dependent variable, that gives you an effect size that's widely used in experiments. That's as distinct from standardized coefficients, where both the y variable and the x variable are standardized. These are sometimes called effect sizes, to add to the confusion. They're sometimes called beta weights. Sometimes people distinguish between B and beta and use beta. They reserve beta to be standardized coefficients. So it's really just doing a double standardization. And if you think about it, this really just takes the raw score coefficient and multiplies it by the ratio you invert and multiply of the standard deviation of x to the standard deviation of y. So, you know, you can tell Stata or SPSS or whatever to give you standardized coefficients. You can also just do the calculation. Get raw score coefficients, find out what the standard deviation of x and y are, get this ratio and just multiply it times the raw score coefficient, gives you the same thing. So let's use an example here. This was part of a data set we used to have for this class. It was a motivation data set in Orange County. In this particular case, the measure of motivation was task value. To what extent do middle school students attach importance to the task of learning math? And let's just say we want to look at it as a function of age. All right, so I've got a big sample, thousands of kids. and we're regressing task value on age. These are middle school kids, age 10 to 15 or so, mean of 12.58. And in this case, the standard deviation of age is 0.64. And motivation is on a 5-point scale. Mean is pretty high, 3.61. Standard deviation is 0.61. If you actually run this regression, you'll get motivation is 5.25 minus 0.14 age. All right, so you plot motivation 0 to 5, that's the scale. And age here, 5, 10, 15, right? The sample is really in this 10 to 15 range. And if age is simply in years, you end up with a intercept of 5.25, which is motivation at 0 age, which doesn't make any sense, but that's what the equation gives you. And then you've got this decline with the slope of minus 0.14. So motivation declines by 0.14 units per year of age. And the question is that a big amount or a small amount? And you can think about these different ways of expressing coefficients as helping you understand that question, right? So one way of transforming the coefficient is to divide by the standard deviation of y, which in this case is 0.61. Keep x naturally scaled because that's age, and an additional year of age has a meaning. So if you standardize the numerator, you want to take 0.14 and divide it by standard deviation of motivation, which is 0.61, which is 0.23 standard deviation, minus 0.23 standard deviation change in motivation with every additional year of age. All right, so for some people, that's a more intuitive way to express it. If you wanted to do a standardized coefficient, you'd have to take the minus 0.14 divided by 0.61 over the change in x, which is 1 divided by the standard deviation of age, which is 0.64, right? Or minus 0.14 times 0.64 over 0.61. Turns out those standard deviations are very similar. So you end up with a standardized coefficient, thoroughly standardized, completely standardized coefficient that's very similar, 0.15. That's the standardized both numerator and denominator. And for some people, that is quite meaningful. Economists like percent change. You know, to what extent on a percentage basis is motivation changing as a function of age? So percent change is just change in y relative to the average of y with each additional year of age. The average is 3.61. So if we express minus 0.14 as a fraction of 3.61, we end up with 3.8%. So it's a minus 3.8% per year of age. Right, we're saying 0.14, how much is that changing as a percentage of the base for y, which is 3.61, and that result is it's falling by 3.8% per year. All right, that may be more intuitive to you. As I say, economists tend to like that. You know, it's a different way of making units free. If you divide by the standard deviation, you know, whatever this 5-point scale was, you're getting away from that 1 to 5 scale by standardizing it and by expressing it as a percentage. So it's a way of trying to develop a measure of effect size that you can compare across other variables in your data set. You can compare to other articles and what sort of relationship they get between, in this case, motivation and age. So let's put these last two on hold here. But you know, I can't say one of these is best because it all depends on the circumstances. And different disciplines use, you know, if you try to explain to an economist about an effect size of 0.2 standard deviations, chances are they're not going to know what you're talking about, right? And if you try to talk about a percentage change to a developmental psychologist, they're going to wonder what you're talking about too. So one of the things that education researchers have to do is to be able to understand how the people they're dealing with, whether they be developmental psychologists or policy people or economists, how do they think about these things? And then you can express whatever you've gotten in the way of results with language that they can understand. Okay, so let me give an example. Paul, you want to pause things?
We're good.
All right, so this was going to be a breakout exercise. So you can do it individually now. This is an article, a paper that Drew, Dick Murnane, and Natalie Young, one of your colleagues, did in November and December of this past year. We were interested in the implications of COVID-19 for the learning gaps between advantaged children and disadvantaged children. So as you probably know, gaps, especially in things like test scores, between high and low income kids are very large. And if you think about the implications of COVID over the last year, they're likely to be pretty significant in terms of their potential for increasing the achievement gap. People won't really know how much that's true until we've got reliable test scores. But we wanted to see what the economics or the education profession, economists as well as public policy people, as well as traditional education researchers, what their best guesses were about how much learning gaps between high and low income kids would increase as a result of the pandemic. And then we wanted to know not only short term, how much they thought they'd increase by a few months from now, spring of 2021, but we also asked about how much of a lingering effect there would be. So we wanted to find out if they thought there was an increase through 2021 from pre-COVID times, how persistent was that increase? It's one thing if it's a very temporary kind of increase, but if you think about the potential problems this coming September, suppose, one hopes that the pandemic is sufficiently conquered that most kids go back to school. Teachers are going to find their classrooms much more heterogeneous than before. Some kids have been able to keep up quite well over the last year. Some kids haven't. So you can think about the importance of things like tutoring programs, things that will help the kids who didn't learn that much this past year catch up. So all that turns on to what extent the gaps are actually going to increase. So I wanted to get some sort of idea, professional opinion about that question. So we did a Qualtrics survey. Natalie did a nice job of setting this up. And you can see what the survey said. Suppose that in early 2020, before the pandemic hit, the achievement gap on a NAEP type math test, in this case we asked about reading also, for children attending elementary school was 1 standard deviation when children in the top quintile, the top 20% of the income distribution, are compared to children in the bottom 20%. All right, that's that 1 standard deviation gap is what a lot of people have found. It shows up in the ECLSK data. It shows up in a lot of other data sets as well. So if going into COVID, the gap was 1 standard deviation, we asked, and these are elementary school kids, we wanted to standardize that to some extent. So we wanted to know to what extent they thought that 1 standard deviation gap would change as a result of COVID. And we did so by saying, suppose that the same children who were pre-COVID at a 1 standard deviation gap were all somehow able to take comparable math achievement tests in spring 2021, in other words, a few months from now. What is your best estimate of the gap estimated from those data? And they just filled in an amount. If they didn't think it was going to increase, they'd say 1.0. If they thought it was going to go up double, they'd say 2.0. So we sent it out to about 200 education researchers, and quite a bit of variability. But research shows that when you look at average predictions from groups of experts, that tends to be to give you information that's really pretty useful. So here's our a very brief summary of our results. The median forecast for the increase in the gap in math achievement in elementary school was from 1 standard deviation to 1.3 standard deviations. The estimate for reading was a little bit smaller, going from 1 standard deviation to 1.25 standard deviations. And then we asked the same thing for a year from now, and things came down a little bit, but not very much. But we faced this task, you're not supposed to look at what I just showed you, of explaining what that increase of 1 standard deviation to 1.3 standard deviations amounted to. Suppose you had to write, this is an executive summary of what you found for a lay audience, not sophisticated researchers. And somehow you had to express that increase of 0.3 standard deviations in a way that people could understand. Okay, so we've talked about different ways of expressing coefficients. This is kind of a coefficient, a 0.3 plus 0.3 standard deviation increase. So the question is, how would you, percentage change, standard deviation change, how would you take that one figure, the 1.3 up from 1.0, and explain it? In other words, finish this sentence. The median forecast for the increase in math achievement in elementary school was a change from 1 to 1.3 standard deviations, dash, a change that, fill in the blank with the words that will best convey the magnitude of that 0.3 standard deviation increase. So I want you to take a little bit of time and think about that. All right. Everybody have a good answer? So this is tough. I don't think most people have any idea what a standard deviation is. You could talk about a 30% increase. That would be more intuitive, probably. What we ended up doing was so a change from 1 to 1.3 standard deviations, a change that is similar in magnitude to half of the amount of math learning that typically occurs across the entire third grade year. A magnitude similar to half the amount of learning that takes place in the third grade year. So we didn't talk about months of learning explicitly before, but we can talk about it now because it's kind of a useful concept. It turns out kids learn at incredibly different rates on standardized tests across the K-12 spectrum. Kindergartners, first graders, if you look at math scores and reading scores, learn about a standard deviation, a full standard deviation on both math and reading, huge amounts. Then things start to slow down a bit. By third grade, you're down to about 0.6 standard deviations of learning across the third grade year. In eighth grade, it's about a third of a standard deviation. Now, a little bit of what's going on is as kids grow older, they tend to learn more specialized things that don't get assessed very well in standardized tests. So that might be part of what's going on. But whatever the reason, you have these different rates of learning. And in third grade, as I say, it's about a 0.6 standard deviation increase. And so what we thought was, if we want to express 0.3 standard deviation amounts in ways that people are going to understand, why not translate it into months of learning, right? So I think people understand if you talk about a child falling a half a year behind, in this case, a low-income child falling a half a year behind, already behind by a lot going into third grade, and the drop is half a year on top of that over the course of third grade as an effect of the pandemic. So that's where we ended up. Maybe it's not the best way to express it, but I think it's a way that people find pretty intuitive. There have been some other studies that have done that. It's a little bit tricky. There's a study looking at the effect of preschool in North Carolina, which was rolled out in the 1990s and 2000s. County by county, and then you could link up counties that receive more funding for this program, and you could look 5, 6 years ahead and see if there's any differential growth in test scores for the cohorts of kids who had more funding for this program, more at 4 is what it's called, than cohorts that had less funding. And what they did, they had test score differences, but they translated it into months of learning. It's a little bit tricky because, as I said, it's about a 0.6 standard deviation increase over 3rd grade, a 0.3 something standard deviation increase over 8th grade. So a given standard deviation increase as an effect is going to look much bigger in 8th grade than it is in 3rd grade, because the amount of learning that takes place is so differential. Anyway, maybe we can, when we reassemble, we can talk about what your answers were. The final rather exotic but very nice way of expressing coefficients is an idea that Artie Goldberger had many years ago. Economists like to think about bang for the buck. To what extent does spending money on different kinds of inputs? Let's say you have $1,000 per child to spend on different inputs into a child's education, right? You can decrease class size, you can increase technology, all sorts of things you can do. You can require teachers having advanced degrees. If you spend $1,000 on each of those things, what is the impact in terms of how much students learn, right? So in that case, you could have a months of learning, or you could have an effect size in the numerator, but the denominator becomes per $1,000 change, right? So you've got to translate a change in X according to its cost in order to get it scaled so that a 1 unit change in X was a $1,000 additional expenditure for X. I've never seen it used. It's one of those things that is great in principle. All right, so that's pretty much it. Let me just say one more thing. Standardized coefficients are very widely used. And they do have advantages. If you so let's say you've got y equals a1 plus b1 x1 plus b2 x2 plus b3 x3. If you, let's say that beta is the standardized coefficient. If you had only a bivariate regression, y equals beta 1 x1, take the standardized coefficient and square it. That equals the R squared. If you look at their how they're calculated, that's what you get. If you have in this 3-variable equation, beta 1 squared plus beta 2 squared plus beta 3 squared, that sums to the R square if the x's are uncorrelated. If they're positively correlated, it sums to less. If they're negatively correlated, it sums to more. But you can see how betas indicate relative explanatory importance. And in our forward causal inference versus reverse causal explanation kind of framework, the reverse causal explanation was all about trying to explain some outcome variable. So having an idea of where the action is, what variables are relatively more important than others in explaining the outcome, that's important. So you see a lot of standardized coefficients being used in the kind of reverse causal explanation articles. So that's one point. A final point. If you're going to standardize, what standard deviation to use? A lot of people use the sample standard deviation. In some cases, there are national norms for test scores, for example, or behavioral indices. So if you've got national norms to tell you what a standard deviation and scale is, that's the best. But if you don't, people often use just the standard deviation for the sample that they have. And that can be misleading. If you look at a very famous it's a very famous preschool program. It's called the Abecedarian program. Very intensive. It was run out of University of North Carolina. Started in the early 1980s. It was a very intensive program. It started at age 6 months, when the kids were age 6 months, and provided 40 hours a week of early education programming with a very well thought through curriculum, all the way up to age 5, their school entry. And Abecedarian had big impacts. It was random assignment. Big impacts on IQ through age 21. The only study that has been found to have long-term effects on IQ. And the impacts were on the order of 0.45 standard deviations. They reported. But they used the sample standard error, right? And it turns out the Abecedarian sample was a uniformly poor sample of kids, and the IQ range was much smaller than it was for the national norms. So they were reporting what looked to be very large effect sizes. This is using sample standard deviation, but it was only about 0.3 standard deviation using national norms. It's not to detract from the fact that it generated significant effects, statistically significant effects, all the way through the teenage years, but it does suggest that you can provide a somewhat misleading estimate of what the impacts are if you have a fairly homogeneous sample where the range on your dependent variable is considerably more constricted than the range you get with the national sample. So that's a disadvantage for using standardized coefficient, because there's this issue of what standard deviation to use. And it's also, this is a pretty obvious point too. We talked about a standardized change in y over standard deviation of y. In an experimental setting, you want to keep x measured in raw units, 0, 1. That's going from being in the control group to being in the treatment group. If you go fully standardized and divide this 1 unit change in x by the standard deviation of x, you lose this very nice interpretation of standardized change in your outcome, going from being in the treatment group, from being in the control group to being in the treatment group. So standardized coefficients aren't very good when you've got an experiment, because it doesn't make any sense to divide by the standard deviation of x. And they can be misleading if you don't pay attention to what standard deviation you're using and whether in fact it's a meaningful standard deviation. Okay, any questions? Okay, your representative, Paul, is saying no. So end of this portion, and we'll talk about dummy variables soon.